Hello everyone. In this video we will discuss about gradient descent algorithm. Gradient descent is a iterative optimization method to find out the minima or maxima of a function. Gradient descent is widely used in the domain of AI, especially in machine learning and deep learning algorithms. Before we see the applications of how gradient descent is applied in ML and DL, first let us see what is general optimization and what are various categories we have and how gradient descent differs from other optimization based techniques. So optimization is a field of mathematics which deals with finding the best possible solution with or without conditions or constraints. So we essentially find out a maxima or a minima of a function across its domain. So broadly, optimization can be categorized into two categories. One is unconstrained optimization and the other is constrained optimization. In an unconstrained optimization, we only have the objective function and the domain can be anything from minus infinity to infinity. Whereas in a constrained optimizations, we have constraints on the domain and our solution should make sure that it satisfies the constraints and also appropriately do perform the optimization. So in unconstrained optimization, we have broadly two different kinds of methods. First methods are analytical methods, which are based on calculus, and the second method is on numerical methods, which are iterative methods. That's where we have this gradient descent, Newton's method, etc. In coming to the constrained optimization, we can broadly categorize it into convex optimization and non-convex optimization. In convex optimization, we have various algorithms like linear programming, quadratic constraint quadratic programming, SOCP, SDP, etc. In non-convex optimization, we have integer programming and various other algorithms comes under non-convex optimization. So gradient descent is mainly applied for the unconstrained optimization, and it is also an iterative approach, and also it gives an approximate solution. We don't get any formula, but we eventually reach to the solution. So let's see the details of how gradient descent works and also how it is applied in ML algorithms. Before we see the working of gradient descent algorithm, let us see some more details of how analytical methods work. So in analytical methods, the function can be a single variable case or a multivariable case. In single variable case, we differentiate the function and equate it to 0, and we obtain a closed form solution for the minima or maxima. And we can know whether it has a minima or maxima by computing the second derivative, and if second derivative is greater than 0, it is having a local minima, and if second derivative is less than 0, then it has a local maxima. And when you go to the two variable case, we have something called as a Hessian matrix, and before that, to obtain the closed form solution, we compute the gradient in a vector form and equate it to 0. And based on this Hessian matrix, which is the partial derivative with respect to x and y, we compute using the determinant D of this Hessian matrix, we compute whether it has a minima or maxima. So these are the conditions which it needs to satisfy. If D is greater than 0, based on fxx value, we can say whether it is minima or maxima. If D is less than 0, saddle point, and if D is equal to 0, we cannot say anything, which is inconclusive. The same idea can be extended to multivariable case, where the Hessian matrix would something like this. First, we compute the gradient and equate it to 0 and obtain the solution. We can later say whether it has a local minima or maxima or a saddle point based upon the determinant of this Hessian matrix. So that was the case in two variable case. In the three variable case, we look for whether this matrix is positive definite or not. We know that H is a symmetric matrix because of the way it is defined, but it is positive definite only when it satisfies this condition, or you can say when all the eigenvalues are greater than 0, and it would be negative definite when all eigenvalues are less than 0, and it satisfies this equation Z transpose H Z less than 0. So whenever it is positive definite, we will have minima, and whenever it is negative definite, we will have maxima. and other cases are whenever it is indefinite we have saddle point, and when h is semi-definite, which is greater than or equal to 0 or less than or equal to 0, then it can be inconclusive. So in this way analytical methods work based upon the first derivative and equating it to 0, and later by using this Hessian matrix and second derivatives we say whether it has local minima or local maxima. So this is how unconstrained optimization analytical methods work. Now let us come to numerical methods. When you come to numerical methods, we have various iterative methods. The first order methods are gradient descent, stochastic gradient descent, conjugate gradient descent. And the second order methods are Newton-Raphson's method, quasi-Newton methods. And we also have stochastic and evolutionary algorithms like genetic algorithms, simulated annealing, particle swarm optimization. And we also have direct search methods or derivative-free methods, which are pattern search and one-dimensional search. So in this video, our main focus would be on gradient descent, which is also a numerical method, which is an iterative method, and it generates an approximate solution. We attempt to learn the details about it and apply the same for ML algorithms. So let us discuss the working of gradient descent algorithm. As I stated earlier, gradient descent is a iterative optimization method which is used to find the local minima or maxima of any differentiable function. The core idea of gradient descent is something as follows. We move in the opposite direction of the gradient to reach to the minima or maxima. And why it works, let us try to understand. Let's consider a function f with a variable w, and let's consider a simple parabolic function, and we don't know exactly where the minima is. Our goal is to find out the w which leads to the minimum value for this particular function. And in order to do that, first we start with some random point, and that random point can be anywhere and it can have any value f of w, and from there we have to take iterative steps to reach to this point minima. And this happens by using this main equation. This is the gradient descent update equation. So this is I indicates the ith iteration and I plus 1 indicates the I plus 1th iteration. So whatever may be the starting point wi, the next step should be in the direction of the negative of the gradient. So what is the use of this negative of the gradient is, so for example, if you find the gradient at a particular point, for example here the gradient is negative. So when the gradient is negative, this negative multiplies with this negative and it becomes the overall positive term, and therefore it moves towards the positive direction, which is to the right side. When the slope or the gradient is positive, so the positive and the negative term, negative symbol becomes negative, and therefore whatever the new value of w will be smaller than the earlier value of w, because we are trying to subtract some term. So when you are towards the positive gradient, you are subtracting, and therefore you will be moving towards the left side. So when the value decreases, we are going to the left side. When the value increases, we are going to the right side. So irrespective of where we start, whether we start towards the right side or left side, based upon the gradient, we can move closer and closer to the minima in an iterative manner. That is the core idea of gradient descent algorithm. So we use the negative sign just to make sure that whatever may be the starting point, our iteratively we should be able to reach to the minima after few iterations. So that's the core idea. So that's how gradient descent works. But the important thing to note is it works for the functions which have a nice minima, only single minima. Otherwise we will struck with local minimas. That's why we always say that gradient descent is used to apply or to find out the local minima. In some cases, for example like convex functions, local minima will be equal to the global minima. So there is no problem. Whatever, if you find the local minima, we eventually claim that we also found the global minima. But that's not the case for functions which are non-convex, where it can get struck to the local minima. So here we have one more parameter, which is eta, which is the learning rate. So how fast you take these steps, iterative steps to reach to these minima, depends upon the value of eta. If the value is smaller, we take smaller steps and it takes many iterations, whereas when eta is larger, too much larger, it kind of oscillates between both the sides before it reaches to the minima. So we have to carefully and heuristically choose neta such that it does not take too long, at the same time it does not oscillate. So that's the learning parameter neta. And finally, when you see, so this is an alternative way of representing this equation. The same gradient has been represented here. So this is what is the gradient descent algorithm. It is an iterative approach to reach to the minima or maxima of a function. So let's take one example. Let's consider this function f of x is equal to x square, which is a nice parabola, and we know that it has minima at x equal to 0. But let's see how gradient descent works for this particular case. And we know this is the update equation of the gradient descent. Xi plus 1 is equal to xi minus eta into the gradient term, and we compute the gradient at each iteration and see how the values changes. So let me consider a random point which is x naught equal to minus 2. We can start from anything. I have started from minus 2, so which is something here. So the corresponding value of f is there is certain value which is definitely not the minima, and I am choosing the learning rate neta is equal to 0.1. So after one iteration, what we get is from x naught equal to minus 2, we reach to x1 is equal to minus 1.6, which means that we are slowly moving towards the right side, because here the gradient is actually negative. So the negative into negative term becomes positive, and therefore it is moving towards the positive side. So when you take the next iteration, it further moves towards positive and became minus 1.28. When you further do one more iteration, we come to minus 1.024. When you do once again, it goes to minus 0.8192, and so on, and we can go until we reach to the minima. But we never actually reach to the exact 0, it only tends to 0. So that's why we say that gradient descent gives the approximate solution in an iterative manner. So in this way gradient descent works. So let us see for a case where the function is not convex, which means that it has both local minima and global minima are not same. So as you know, by seeing the figure we can say that the minima is here. But what if you start the point from here? If you start from the point here, we eventually settle to this local minima, and which is definitely not the solution which we want. So we usually expect some form of a global minima. So but this is the kind of limitation of the gradient descent which only allows us to find out the local minima. So suppose that we choose the point from here. So this is how it actually moves, and if you start at this point, it actually nicely try to reach to the optimum. Otherwise we might settle with any of these two local minimas. So this is one other example for functions which are not convex. So let us discuss now when gradient descent method is useful and when analytical methods are used. So in machine learning, whenever a particular algorithm exhibits a closed form solution, we look for a analytical solution where we derive, do the mathematics and compute the equation closed form solution for that particular variable. But whenever there is no feasibility of closed form solution, we apply the iterative approaches like gradient descent method. So that is one case, and in second cases, when the computing closed form solution becomes too expensive in terms of computation. For example, let's take this linear regression model. We minimize this mean squared error between the actual output and the predicted output. So there is an error between them, the epsilon, and we try to minimize the L2 norm of that error. So when you do that, this is what is the closed form solution which we get. But when the X matrix is bigger or X transpose X is big, then computing this inverse can be sometimes challenging. In such situations also we follow the iterative methods to compute the solution. So these are the two cases when we follow the gradient descent method. In the first case, there are situations where there is no closed form solution, and we are forced to follow the iterative methods, and in the second, it is due to the complexity we choose the iterative methods. So now let us see how gradient descent is applied for various algorithms in ML. So we know the gradient descent update equation. So weights are the parameters or the unknowns which we would like to find, and we know that in gradient descent we randomly initialize and we iterate for few iterations until we reach to a point where we have a minimum for the function j. So this is the update equation, and this is the vector form if the variable is our vector. So this is the vector form of gradient descent. So let's see a few algorithms where it is applied. As I stated earlier, so in linear regression or multiple linear regression or polynomial regression, we encounter a system of linear equations and they exhibit an error, and we try to minimize the squared error. And this is what is the squared error, which is represented as the L2 norm. And this is how the update equation looks like. So we compute the gradient of this error and equate it to gradient. We compute the gradient, and this gradient term is what shown here. And this is the vector form of update equations for multiple linear regression and also polynomial regression. So when you come to the logistic regression, the cost function is different. Here we use categorical cross entropy as the cost function, and the update equations look something like this. So we compute this loss function dou L by dou Wj, and in our previous video we have shown the complete derivation of how we compute this gradient by using the chain rule, and finally we obtain this update equation. So here also we apply the gradient descent algorithm to update weights and biases in logistic regression. And in neural network, these are the update equation to compute the weights of the neural network. We compute the gradient with respect to W and gradient with respect to B, and obtain the optimal weights and biases by iteratively updating the terms. So these are the other terms. The more details are explained in the neural networks video. You can go through it. So in summary, gradient descent has a number of applications in machine learning, and it is an iterative approach where iteratively it updates the parameter values to reach to a point where the cost function has some form of minima. So it is very useful, and this is how the current state of the art neural networks and all ML algorithms are using. There are variants of gradient descent like stochastic gradient descent, mini batch gradient descent. Conceptually they are just similar. It's just about when we are trying to update the value. Rather than updating for every possible iteration, we update over a period of samples or a particular batch of values, except that the conceptually they are similar. So this is about gradient descent algorithm, which is one of the iterative approach or one of the numerical method to find out solution to the unconstrained optimization problems. Thank you.